We're going to be moving on to graphing systems of linear equations. So the section before this, 5.7, was only graphing one inequality on a coordinate plane. Now we're going to do a system, which means we're going to have more than one. So how are we going to determine the solution of this, of a system of linear inequalities? How do you determine the solution to a system of linear inequalities? I would highly recommend that you actually have maybe some different colors to use, because we're going to be shading a couple different things at once. So for example, for our first system of equations, we'll be doing 2 on the same coordinate plane. We're going to graph these two equations. 2x plus y is less than or equal to 10, and negative 2x plus 2y is less than 8 on the same coordinate plane. So we're going to see how that works. First, we're going to actually graph this equation, and I'm going to just solve this for y quickly by subtracting 2x on both sides. So it cancels that. And we get y is less than or equal to negative 2x plus 10. That's easily graphed by starting at 10 on the y-axis. That's your y-intercept. And we're going to go down 2 over 1. That's your slope. Down 2 over 1. Down 2 over 1. Again, if you have a colored pencil or something like that, we're going to use 2 different colors here. One for this graph and one for the other. I'll change the color as well. And it's also helpful to use a ruler or some kind of straight edge to draw these, because we really want to see where these two lines are going to intersect. So as best as I can, this is less than or equal to, so we need to draw a solid line as best we can. That's why I need to have a bunch of dots, because I can't draw very straight lines. For part B, we're going to use a test point, like we did in the last section, to figure out where to shade. Now, you might be able to look at this and say, oh, I know where to shade. It should be below the line somewhere. So let's see if that actually works. I'm going to pick 0, 0 like I always do. If I plug in 0, 0, it'd be 0 is less than or equal to negative 2 times 0 plus 10, which is the same thing as 0 is less than or equal to. That goes away. It just becomes 10. Is 0 less than or equal to 10? Yes, 0 is smaller. So we're going to shade this side here. I guess this time we're going to practice shading it all at once. So using my highlighter, it's going to be less than, so it's going to be below the line, which we already said, as best we can. I don't know why it's not picking up correctly here. Hopefully you can shade that a little better than I did. So it's quite a lot of the graph here. All right, then we're going to do the same thing, but now it's a different equation. Negative 2x plus 2y is less than 8. Change colors. We're going to solve this for y. So let's add 2x to both sides. So that goes away. We get 2y is less than 2x plus 8. And then to get y by itself, we're going to divide both sides by 2. Everything is divided by 2. Remember, at some point you have to change the inequality, but that's only if we divide by a negative or multiply by a negative, and we have not done that here, so that stays the same as less than. 2 divided by 2 is just 1x. 8 divided by 2 is 4. So to graph this one in a different color, we start at 4, and then we're going to go up 1 over 1. So up 1 over 1 here, up 1 over 1 here, so on. And then it also goes down, same way. Down 1 to the left, down 1 to the left. Once you have a couple dots, you can use a straight edge to connect them. Okay. And now if you look at the line here, this is a less than, so it is not less than or equal to. This is going to be a dashed line. Try to represent it as a dashed line. And this sign is less than, so it should be below this line. So it's all going to be down here. But just to double check, I can use 0, 0 as a test point again. Is 0 less than 1 times 0 plus 4. Is 0 less than 1 times 0 is 0 plus 4? Is 0 less than 4? Yes, it is. So we're going to shade everywhere down below. So I'm going to change my highlighter, and we'll shade everywhere down below. As best we can. Yours will look much better than mine, I'm sure. There we go. Oh, part D is what we just did. Use a test point and shade the solution of the different color. So that actually should have been down here for part D. So what is the answer? I mean, you just have all this, almost this entire thing shaded. What is the actual solution to the system of equations when we have these two equations or inequalities? That kind of leads us into this question here. What do you think the different colors of the shading represent? Specifically where the colors overlap. So if we look at the colors where they overlap, I'm not sure if you can tell that it's slightly different. We have blue and red, so it kind of looks like it's a purplish down here. This portion down here, which maybe I can go over with a different color, where they overlap, so we're below the red and below the blue, is only specifically here. Where they overlap specifically is the actual solution to the inequality. These are all the combinations that you can use. There's quite a lot of them, right? All these points in here, all these dots in here, are all the combinations you could use to satisfy both inequalities. So before, when we were just drawing two lines that intersected, right, we just said that there was one solution because they intersected one place. But now, since we're shading part of the entire coordinate plane, now we're getting many different options. So you could pick any of these points here, plug them in for x and y, and it should be true statements for both of them. This is what they call the feasible region. So what do you think the different colors of shading represent, where the colors overlap? That's actually the solution to the system. Come on, of equations. Now, you don't have to actually shade the entire amount for both of these. I didn't have to shade everything in blue and everything in red and see where they intersected. I kind of want to get to the point where we don't have to do that every single time. You can just graph each line and then figure out where to shade in the final area and then just shade one place. So as you practice it, you'll get better doing that. So it's called the feasible region. So what is it specifically? So that would be the colored area of the graph. It's considered to be the solution to a system of linear inequalities. So really the final area that you should have, if I were to go back real quick, technically, the final answer, oops, it's a little too big. To be technical about it, ooh, I wonder if I shouldn't have any of this shaded, and I wouldn't have any of this shaded. The final answer, technically, is just the feasible region, which is inside this area. So I'll go back to this now. So when I say about the colored area, it's actually the final place where they overlap. So this is where the shading of the different colors overlap. But normally, whenever you see a finished one, it will only be shaded in one spot, and that is considered the feasible region. In other words, this is like your solution, right? Same thing. Feasible region. So now we're going to do one with 3. Some of these are pretty easy though. Everything has y on the left-hand side, so we don't have to solve anything. We can just immediately start graphing them. So I'm going to use 3 different colors for this one. It says graph the inequalities on the same coordinate plane to determine the feasible region. The new word there. Be sure to use test points for each inequality to know where to shade. Okay, so we'll do the first one in blue. Y is greater than -1/2 x, so there's no y-intercept here. It'd be plus 0. So I'm going to start at 0, and we're going to go down 1 over 2. Down 1 over 2, down 1 over 2. Oh, I hate when it does that. And up 1 over 2. Again, we have to be very specific because I don't really know where they're going to intersect. So these need to be very good lines as best as possible. Since it's just the greater than, we don't have an equal sign. This is going to be a dash line. So I just throw some dashes where the dots are. There we go. So here's our first one. Y is greater than negative 1/2 x. And then it says greater than, so I'm going to use a quick test point. Now we can't use 0, 0, but you should also know that greater than means it's going to be shaded above the line. We could use something different though. Let's just use 2, 2 maybe. If I use that as a test point, 2, 2, that would be 2 is greater than negative 1/2 times 2. Is 2 bigger than, this would end up being negative 1? Yes, it is, so it does get shaded up here. So what I'm going to do this time around is I'm not going to shade everything. I'm just going to note that you shade above. I'm just going to put a little bit of arrows, just saying I'm going to shade up this direction. I'll take them out later. So right now I have everything shaded up here. But we want to see where all three of these intersect or overlap. All right, change colors. I'm going to go to the second one. Y is less than or equal to 1/2 x plus 4. So we're going to start at 4. And now we're going to go up 1 over 2, like this. Up 1 over 2. Up 1 over 2. And then down 1 to the left 2. There we go. Got to be precise. This has a less than or equal to sign on it, so we are actually going to connect them and draw a straight line all the way through. Like that. So this one is y is less than or equal to 1/2 x plus 4. So when you see the less than sign, we should be thinking it's below the line, so it should be down here. I'm going to put little arrows. I will also use a test point just to make sure. So let's use 0, 0, because we can use that in this case because the red line is not on 0, 0. So I would say 0 is less than or equal to 1/2 times 0 plus 4. 0 is less than or equal to, that goes away, 4. True or false, 0 is less than 4, so we do shade down below. So I'm just going to kind of see where these intersect, where these two intersect right now. So if I'm shading above the blue and below the red, think about where that's at. It's going to be right in here so far, right in this area. It's like a triangle right here. That's where they overlap so far. But we have one more left, and I'm going to do that, let's see, in green. Hopefully you can see that one. It's really bright. Y is less than or equal to 6. If you remember how to graph that from yesterday, we're going to start at 6 on the y-axis, because it's y is less than or equal to. So 6 on the y-axis, and then if you remember, this means it's actually going to be a horizontal line staying through 6, and it has less than or equal to, so it's going to be a solid line going straight through, like this. So this one is y is less than or equal to 6. If I were to use a test point, I can use 0, 0. It's down below here. 0 is less than or equal to 6. That is true, so it's going to be shaded down below. So I'm going to put little arrows here. Like that. So now we have to really see where they all overlap. If we're below the green, we're below the red, so we're kind of stuck in this little spot here, but we are above the blue. So it's kind of like that triangle like it was before, but now this green is kind of cutting off a little bit. So I'm going to shade in yellow my final answer. It's below the green, below the red, but it is above the blue. So here we got this. You can shade a little bit better. It's not supposed to go outside the line. I did a little bit down here at the bottom. This would be considered our feasible region. Oh, I should probably change a different color. Let's do black. This is called the feasible feasible region. It satisfies all three of the inequalities. So again, any of the points you pick in here would satisfy all these inequalities and all be true statements. The last thing we got to do is label something called the vertices of the feasible region. So this would be where the lines intersect each other around the place that's shaded. So let me point this out. We have the green intersecting the red right here, right? They intersect right there, and it's around the border of the shaded area. So we have to label this point, which I believe is 4, 6. So this would be a vertice of the feasible region. And if we keep going, the red and blue intersect right here. This is why it's crucial to make them perfect and exact. This would be -4. We'll squeeze that in there. -4, 2. So the vertices of the feasible region would be -4, 2 and 4, 6. Now, if you look over here, the green and the blue will eventually intersect, but we don't care about those two intersection points because it's not around the feasible region. The only place that these two lines intersect, period, as far as the green and the red and the blue, the only two places that happens around the feasible region are these 2 points here that I labeled. They call them the vertices of the feasible region. All right, everything else you guys can do for the huddle. You got 3 or 4 problems. The only last thing I want to go over is like next to the last problem here. If we go to the very back, the team mastery, there's an A, B, and a number 2 and 3. 3 is a challenge problem. You don't have to do it. I can't even spell the word challenge here. It's messing up. This is a challenge problem. You don't have to do number 3, and number 2 we'll do together. So if you see this one, there's 2 lines. There's 2 different lines here. But there's only one shaded area. So I'm going to practice this one and then finish up. So I'm going to do the first line here. These are both solid, so we're going to have equal signs on each one. So how about this one here? See where it crosses the y-axis? That's at -2, I believe. So we're making a system. Got to have curly brackets. It's going to be y, and this one starts at -2. So I'm going to leave this middle part here blank, and then we're going to start at -2. So it starts at -2, and then we have an x. We got to figure out what the slope is. Where does it go through perfectly? I feel like it goes through right here. So we can count blocks from one to the other. We're going to go up 1, 2, 3, 4, over 1, 2, 3. Looks like it's 4 over 3 is your slope. We don't actually have anywhere else where it crosses perfectly, so that's got to be it. And then if we're shading above the line, right, this way, we're going to assume that that's going to be a greater than or equal to. So I'll fill that in over here. Greater than or equal to. And that should work. If I use a test point, I'm going to go off the side and use a 0, 0 of where it should be a true statement. 0 is greater than or equal to 4/3 times 0 minus 2. Is 0 bigger than or equal to, that goes away, -2? Sure is. 0 is bigger, so I shaded the right area and chose greater than or equal to as the right sign. All right, the other one, might as well change colors. This one goes through the y-axis at, looks like -4. That one was -2. This is -4. So we're going to have y, we're going to have -4 at the end. We have to have our x value. What's the slope? It looks like we go up here. They intersect right there. If you can see it. Looks like the slope would be down 1 block over to the right 3. Down 1, 1, 2, 3. Looks like it's a down 1 means negative, so it's going to be -1 to the right 3. Or if you think about it the other way, it would be going up 1, positive, but then to the left 3, which would be negative. So as long as the negative's on one of the numbers, it doesn't matter. And then this one looks like we're shading above the line again, because it's shaded up here. So that looks like that's also going to be a greater than or equal to. It's a solid line, so equal to has to be on there. This one you can also test 0, 0 again. So I'll do that off the side. 0 is greater than or equal to -1/3. We want this to be true. 1/3 times 0 minus 4. 0 is greater than or equal to, that goes away, -4. 0 is bigger than negative 4, so that's correct. So this would be your system of inequalities. It doesn't ask about the it does not ask about the vertices of the feasible region, but you can figure that out. That actually ends up being the point right here. Although it's not clear as to what that point is, it's around -1, negative 3.7 or so. But we don't know this point. But that would be the only point of the feasible region. So now you should have enough information to finish off the mastery and the huddle. Again, this is the challenge problem, but you need to go back and do A and B for number 1. Careful when you have these numbers here, x is greater than or equal to 0, and this last one here, x is less than 6. That means that these are vertical lines, not horizontal lines. And then you should be able to finish the rest of those. And everything will be sent and turned in for the notes.